Now that we've had a brief overview of organic reactions, we're going to take a closer look at polar reactions. We'll talk about some general information, look at an example, and really focus on curved arrows. With polar reactions, we are talking about the movement of a pair of electrons. And most of the reactions that we'll be talking about in this entire year of organic chemistry will be polar reactions. We represent the movement of a pair of electrons using a double barbed arrow. We start from the original location of the electrons and we point to the final location of the electrons. So what we're looking at then would be heterolytic or unsymmetrical bond breaking. So when we have a pair of electrons, rather than one going one way and one going another way so that the bond breaks symmetrically, this is unsymmetrical so that both electrons are going to go in one direction. So for example, if these electrons move on to B, what this arrow says is that this pair of electrons that used to be shared between A and B move on to B, which gives us A plus B. B now has a new lone pair. This lone pair is what used to be this shared pair. Because these started out neutral, I'm not being specific, it's just a generic A and B, but if this started neutral and then it lost an electron, then this would have a positive formal charge. And if B started neutral and gained an electron, then this would have a negative formal charge. But one of the important things to notice is that both electrons of the bond move on to the same atom. We can also think about unsymmetrical bond forming. So we can start with a pair of electrons, and these can both move onto the X. Now, this doesn't mean that the electrons just hop over. It means that this pair of electrons that used to be owned by the W are now being shared with X. So this gives us a new bond between W and X, where this pair of electrons is now this pair of electrons. If we started out where W and X were both neutral, well, W lost an electron, so now this would have a positive formal charge. X gained an electron, so now this would have a negative formal charge. As another example, we can have Y sharing electrons with Z. So this pair of electrons would be shared with Z, which gives us a new bond between Y and Z. So this pair of electrons of the bond is what used to be this lone pair of electrons. So in both of these cases, both electrons of the bond came from a single atom. Another thing I want you to notice is that for any reaction, the charge on the left side will be the same as the overall charge on the right side. Here, these are neutral, so the overall charge is 0. Here we have a formal charge of +1 and -1, which gives us 0. We start out with 0, we end up with 0. We start out with 0, and we end with 0. Whenever we are thinking about polar reactions, we need to think about something that is electron rich sharing electrons with something that is electron poor. So we need to think about polarity and the existence of polar bonds in our starting materials so that we can identify who's electron rich, who's going to share their electrons with somebody that's electron poor. Now, some bonds are inherently polar. We've talked about electronegativity differences, so Falkland-Birch, where carbon, is about the same as hydrogen. But fluorine is more electronegative than oxygen, is more electronegative than chlorine, nitrogen, etc. So if we have a carbon-fluorine bond, then we know that fluorine is more electronegative, so we can draw a dipole arrow, or else we could represent this where the carbon has a partial plus and the fluorine has a partial minus. If we have a carbon-oxygen bond, we know that oxygen is more electronegative than carbon, so we can draw a dipole arrow that looks like this. Or we can think about the carbon having a partial positive and the oxygen having a partial negative. Remember, with our dipole arrows, we can draw them parallel to the bond that we're talking about. And we point to the atom that is more electronegative. And then on the back end, we have the plus, which reminds us that the fluorine is stealing away electrons from the carbon, leaving the fluorine electron rich and the carbon electron poor. Now, some bonds may have enhanced polarity, for example, due to an acid-base reaction. If we were to think about methoxide, so this is the conjugate base of methanol, compared to methanol itself, compared to the conjugate acid of methanol. So if methoxide acts as a base and grabs a proton, then we get methanol. If methanol acts as a base and grabs a proton, then we get the protonated methanol. Now here, oxygen has a negative formal charge, and we know that oxygen is more electronegative than that carbon, so it is going to be pulling electron density away from the carbon as well. So this oxygen definitely has negative character and the carbon has positive character. In the case of methanol, we have no formal charges, but we know that oxygen is very electronegative, so it is pulling away electron density from the carbon and it's pulling electron density away from the hydrogen. So although there are no formal charges, this oxygen is still going to have a partial minus, the carbon has a partial plus, and the hydrogen has a partial plus as well. In this case, oxygen has a formal charge of +1, but oxygen is still electronegative. So the formal charge is about bookkeeping, but in reality, we know that oxygen is still going to be pulling electron density away from the carbon and both hydrogens. So the hydrogens and the carbon are actually going to have the partial plus so that the oxygen doesn't really have a full positive charge. Now, if we were to focus on the carbon in these three species, here the oxygen is stealing electron density away from the carbon, but because it has a negative formal charge, maybe that's going to leave this carbon with a small partial plus. Here, the oxygen is going to be pulling harder, so maybe now it is a bigger partial plus on the carbon. And in this case, because oxygen is really going to be pulling away electron density from the carbon, now we're going to have a really big partial plus. So this carbon has enhanced polarity. It has a bigger partial positive because this oxygen is more desperately pulling away electron density. And finally, we need to consider the fact that some bonds are very polarizable. So polarizability is kind of a measure of the response by an atom to changes in the electric field. Maybe it's because of solvent, maybe it's because of other polar molecules, but can those electrons fluctuate in response to something else? Well, if we are looking at something like carbon-hydrogen compared to a carbon-iodine bond, well, in the case of carbon with hydrogen, okay, we have this electron cloud. This is where those electrons exist. So what we draw as a bond, in reality, this is a cloud of electrons. This is the orbitals where those electrons exist. In the case of carbon iodine, now we have a really, really big cloud because the iodine is so huge. Well, within this smaller cloud, there's not really a lot of shifting can happen. So if an anion approaches, then there's not really much that can happen here. Whereas on the other hand, let's say we have some anion that's approaching from here, well, these electrons can kind of gather over on this side. And therefore, this takes on a much bigger partial plus, partial minus because of the fluctuation of electrons, because this bond is much more polarizable than this bond. So another way to think about this, let's say because of electronegativity differences, maybe So just based on electronegativity, maybe we would expect a partial plus and a partial minus to be this particular size. Well then, if we take into consideration polarizability, maybe this takes on a big partial minus and a big partial plus. Please note, it's only as I'm talking through this that I'm trying to make a specific comparison using a bigger delta to represent more partial positive character. If I just happen to, draw something this big, then I'm not really trying to make a comparison. So just be careful of that. Early this semester, we talked about Lewis bases and Lewis acids, and we introduced the terms nucleophiles and electrophiles. A nucleophile loves a nucleus. So remember, a nucleus has a positive charge, therefore something that loves a positive charge would itself have negative character. An electrophile is something that loves electrons. So it loves something with negative charge, therefore it has positive character. Keep in mind the symbols that I use, the shorthand for a nucleophile is this, because having this lone pair reminds me that a nucleophile tends to have extra electron density that it wants to share. And for an electrophile, I use this as my shorthand. Although I write it with a positive charge, I want this to represent positive character because a nucleophile will share electrons with an electrophile. A nucleophile is electron rich, an electrophile is electron poor, so the electron rich nucleophile shares electrons with the electron poor electrophile. So for example, if we have some W sharing electrons with X, in this case, W is the nucleophile and X is the electrophile. We had another example where Y minus shared electrons with Z, and in this case, the Y minus is the nucleophile and Z is the electrophile. So a nucleophile might have a negative charge or it might be neutral, but in general, it's going to have negative character. So either negative or maybe this has a partial negative. An electrophile, on the other hand, will either have a positive charge or be neutral, but if it's neutral, it may still have a partial positive charge, if not a full positive. Now, in organic chemistry, we have some very common nucleophiles. In many cases, it's going to be something with a lone pair. So it could be ammonia, or it could be an amine, where this nitrogen is connected to some alkyl group. Because we have this lone pair, we have nucleophiles. Water is a good nucleophile. Hydroxide is an even better nucleophile. In addition to species that have lone pairs, which may either be neutral or negatively charged, double bonds can also be nucleophiles because this is electron rich, and so these electrons can be shared with somebody who is electron poor. Some common electrophiles could be things like H3O+, it could be some alkyl halide, because bromine is more electronegative than carbon. That means it's pulling away electron density, which leaves a partial plus on the carbon and a partial minus on the bromine. So the carbon is the electrophilic atom. Now, another species that we're going to see a lot will be things that contain a carbonyl. So if we have, for example, a ketone. So remember, a ketone has a carbonyl, a C double bond O, and then the carbonyl carbon is connected to two other carbons. Although there's no formal charge on any of the atoms, because oxygen is more electronegative than carbon, this is going to have a partial plus, and the oxygen is going to have a partial minus. So the oxygen can act as a nucleophile, whereas the carbon can act as an electrophile. We're going to see examples of both types of these reactions. Now that we've talked about polar reactions in general, let's take a look at a specific example. And we'll be focusing on the electrophilic addition of HBr to ethylene. So this is ethylene. It is an alkene, and it is going to react with HBr to form bromoethane. So these electrons are going to be shared. So this is the nucleophile, and this is the electrophile. So focusing on the overall reaction, we see that this is an addition because the hydrogen and the bromine are adding across the double bond, and so we go from these two molecules to one molecule. Now the mechanism of this reaction, it is a polar mechanism. Now with the double bond, this is very electron rich. So let's think about this. We have the carbon and the other carbon. These carbons are sp2 hybridized. So we have a sigma bond created by the overlap of an sp2 orbital with another carbon sp2 orbital. That's what gives us the sigma bond. But we also have a pi bond that's created by overlap of the p orbitals. So we have electron density above and below the plane, as well as electron density along the axis that joins the atoms. So overall, lots of electron density, which makes this electron rich, which means it can act as a nucleophile. As a nucleophile, it is going to share electrons with something that is electrophilic. If we look at HBr, we know that bromine is more electronegative than hydrogen. So that means that we can draw a dipole arrow, or we could show that the bromine is partial minus and the hydrogen is partial plus. So we have our nucleophile and we have our electrophile. More specifically, this is our electrophilic atom. So the nucleophile can share electrons with the hydrogen, which would then push these electrons onto the bromine. So let's say that the carbon on the left is the one that becomes connected to the hydrogen, and the carbon on the right is the one that lost its electrons. That means that the carbon on the right is now a carbocation. So this carbon has a formal charge of +1. And then we also have Br minus. So this pair of electrons that used to be shared between the hydrogen and the bromine, that's now an extra lone pair of electrons. So the bromine has a negative formal charge. We start out with both species neutral. We end up with a positive and a negative, which gives us a total charge of 0. So 0 on the left, 0 on the right. In this first step, our carbon-carbon pi bond is breaking while our carbon-hydrogen bond is forming, while our hydrogen-bromine bond is breaking. So we have both bond breaking and bond forming happening at the same time. Now, in the second step, our species have changed roles because now the bromine is electron rich, and our alkyl group, this is electron poor. So now the Br minus is the nucleophile, and while up here this was the electrophile, now this is the electrophile. More specifically, the bromine can share its electrons with this carbon. So the bromine shares electrons with this carbon, and then that gives us our hydrogen, which originally came from the HBr, is connected to this carbon, and then that carbon is now connected to the bromine, which still has its 3 lone pairs, but this lone pair is now this bonding pair. In the first step of the reaction, we had both bond breaking and bond forming. In the second step of the reaction, we have only bond forming. Let's focus again on the use of the arrows. So remember, the arrows represent the movement of electrons. So this pair of electrons, instead of being shared between this carbon and this carbon, they remain associated with this carbon, who now shares it with the hydrogen instead. So the carbon on the left is connected to the hydrogen. This pair of electrons moved on to the bromine, and so there's this extra lone pair on the bromine. The arrows represent the movement of electrons. Once you have shown the bonding changes, you must also think about formal charge. Here, carbon was connected to 4 groups, and it had a formal charge of 0. Here, carbon has only 3 bonds. So when we think about formal charge, on the periodic table, carbon wants 4 electrons. Here, it owns only 3 electrons, so it has a formal charge of +1. Bromine wants 7, it owns 8, so bromine has a formal charge of -1. Arrows show the movement of electrons. We represent the bonding changes, and then we assign formal charge. We never, ever, ever use arrows to show the movement of a charge. Okay, we want to focus on starting our arrow at the original location of electrons, ending our arrow at the final location. Starting our arrow at the original location, ending our arrow at the final location. Over here, our arrow starts at the original location of the electrons, and it points to the final location of the electrons. Finally, let's focus even more on the use of curved arrows in polar reactions. So with polar reactions, we're talking about the movement of a pair of electrons. So we're always using the double barbed arrow. So we might represent bond breaking as happening like this, where both electrons move to the same atom, and that would give us A plus plus B minus. So both of these electrons moved onto the B. When we have bond forming, we might see something like this, where an arrow starts at the lone pair and points to an atom, which means this lone pair is becoming a shared pair between W and X. So this gives a new bond between the W and the X. And in this case, the W would take on a partial plus, the X would take on a partial minus. So in a particular reaction step, we might have only bond breaking, we might have only bond forming, or we might have both happening at the same time. Y can share its electrons with A, pushing these electrons onto B, which gives us Y connected to A, no longer connected to B. This lone pair is now the shared pair between Y and A. This shared pair is now the lone pair on B. Y started out negative and it shared electrons, so now it's neutral. A gained and lost electrons, so this is still neutral. B gained electrons, so B must have a negative formal charge. Now there are some rules or generalities that we need to think about. When it comes to polar reactions, electrons always move from the nucleophile to the electrophile. So the nucleophile could be a lone pair or it could be a multiple bond. And the electrophile is something that is able to accept a pair of electrons. The nucleophile can be either negative or neutral, and the electrophile can be either positive or neutral. And finally, we have to keep in mind that the octet rule must be followed. So for example, if A is obeying the octet rule, then as electrons are being shared with it, it's gaining electrons, so it also has to lose electrons at the same time. right? I like to think of it as these electrons come here pushing away these electrons. Or another way you can think about it is that if electrons move to an atom with an octet, another pair must simultaneously move away. So if electrons move to an atom with an octet, additional electrons must move away at the same time. So for example, if we're looking at this or this, if we have a nucleophile and it is sharing electrons with the carbon, then the bromine has to leave. Or if our nucleophile is sharing electrons with this carbon, then these electrons have to move on to the oxygen, for example. This takes care of our introduction to polar reactions, but please take your time trying to understand how we represent the movement of electrons, why we represent the movement of electrons, and this is going to really help as we start learning the specific reactions.